So, hello and welcome to today's Special Relativity lecture. Today we want to finish off our discussions on tensors of special relativity. That appendix by Wolfgang Rindler on tensors of special relativity will conclude our mid-course interlude where we introduce tensors, and we'll then speak in tensorial language for the remainder of the course. Having done that, we'll introduce the concept of space-time and four tensors, the tensorial description of the physical world in which the rest of the course is couched. And lastly, we'll revisit the concept of a world line from a sophisticated perspective, and also light cones. So let's begin by concluding our discussions on tensors. And the numbering I'm using here is the numbering from Rindler's appendix. So tensor algebra, we're going to have 5 different elements of tensor algebra, 5 different elements of tensor algebra, of which 4 are covered in this section. And I'm just going to do it by example. The first is going to be the sum. Now, the key point regarding tensor algebra, and what I'm about to say is trivially provable from the definition of a tensor. And remember, a tensor is a tensor if it transforms as a tensor, and we learned how tensors transformed in the previous class. All of the elements of tensor algebra that I'll give you today have the property of producing tensors from tensors. Just to repeat, all the elements of tensor algebra that we'll go through today have the property of producing tensors from tensors. And I'm not proving it because it's trivial to prove yourself. If the proof takes any more than 2 lines, that's too many. And most of the proofs take 1 line. So let's consider the sum of tensors. Now, in order to be able to add tensors, I want to have them have the same valence and the same free indices. And we make a distinction between upstairs and downstairs indices, between superscripts and subscripts, between contravariant and covariant indices, as we mentioned in the previous class. In order to be able to add 2 tensors, I'm going to want them to have the same indices, upstairs and downstairs. Their relative positions might actually be different, but I want the same number of free upstairs indices and labels, and similarly for the downstairs indices. If A is a tensor and B is a tensor, then the sum of the 2, which is obtained by adding the components in some frame of reference, the sum of the 2 will also be a tensor with the same indices. And the point is that we add these components in some particular frame of reference, we add them, and if A and B are tensors, then C will be a tensor. So much for the sum of tensors. The second of 4 tensor properties to be considered in this section is what's called outer product. So 2 is outer product. If I give you 2 tensors, A and B, and they have a bunch of indices, for example, I, J, K, L, M, and I can put them wherever I want. The point is these are a series of free indices. We don't have any repeated upstairs and downstairs indices, hence there's no implied summation. If A is a tensor and B is a tensor, then if we multiply these things component-wise, we would get a third tensor C, and that third tensor C would have all of the indices hanging off the tensors that have been multiplied. Again, as with all the elements of tensor algebra, this so-called outer product has the property of producing tensors from tensors. The third example of tensor algebra I want to give in this section is called contraction. So tensor contraction. If I was to take some tensor, for example, B, I, J, K, L, M, let's say, for the sake of argument, and if I was to take any pair of upstairs and downstairs indices, for example, K and M, and what I'm going to do is make them the same. So I have the K upstairs, but I'm replacing the M downstairs with a K. So there's now an implied sum over the K. And again, this is a dummy index now. I could call this K and K, I could call it P and P, I could call it filled in circle and filled in circle if I wanted to. It makes no difference. It's summed over, it's gone, it doesn't exist. And since it's summed over, it's gone, it doesn't exist, I'll actually have a new tensor which I call C, which has just the free indices I, J, and L. So this process of taking a tensor, such as this, contracting or summing over a pair of upstairs and downstairs free indices has the action of producing a new tensor. And I'm giving examples of these. Again, this has the property of producing tensors from tensors. In fact, it reduces the valence of a tensor. It reduces the process of contraction, reduces the valence of a tensor. The last example of tensor algebra, for this section, there'll be a fifth which comes later, is called index permutation. And when I index permute a tensor, for example, I take a tensor Aij, and I just ask the question, let me flick the indices around. If I flick the indices around, is this still a tensor? And the answer is yes. And if I wanted to, I could give that tensor a new name, which is B. The point is, if you flick indices around, you actually get a different tensor, but this action of permuting indices has the action of producing tensors from tensors. And the key point here is that we have 4 of the 5 elements of tensor algebra. Now let's ask the question about differentiating tensors. We have a definition of tensors. We've got under our belts now 4 different elements of tensor algebra: sum, outer product, contraction, and index permutation. And all of these elements of tensor algebra will produce tensors from tensors. In other words, objects that transform as tensors. Question: is the derivative of a tensor a tensor? We're passing from tensor algebra to tensor calculus, and if we want to tensorialize the physical world, we're going to be expecting differential equations, so we're going to need tensor calculus. Question: is a derivative of a tensor a tensor? Now the answer is in general no, right? And this is, by the way, the point. Partway through this section, we're going to have a crossroads, where if you follow the left path, the more general path, that will be the path of general relativity. If you follow the right path, the more specialized path, the special path, then you'll have the path of special relativity. In general, derivative of a tensor is not a tensor, but we'll find that for our special case, which is tensors in space-time, derivative of a tensor will be a tensor, but that's not true in general. So let's ask the question about how to differentiate tensors. Now, I just want to revise the common notation that I mentioned earlier. So here's an arbitrary mixed rank tensor with a series of indices I through k and L through n. Now, I've lined these all up in a row. You could do this kind of stuff where you have 1 column for each index. Up to you. Here we have our arbitrary mixed rank tensor, and we know that's a tensor because I'm telling you it is. I'm saying this is a tensor by assumption. But the question is, if I differentiate it with respect to a particular space-time coordinate, remember we're still in our n-dimensional space, which is coordinatized by a series of coordinates, x1 through xn. The n coordinates in some coordinate system are in our capital N-dimensional space. And here we're differentiating with respect to one of those coordinates. The common notation would just say, write out your object again, which we know to be a tensor. And instead of, remember that the R superscript in the denominator is the same as a subscript, and so the notation, the dense notation, is that when we differentiate with respect to R superscript, that becomes a comma denoting partial derivative, and the R downstairs. Question: is this object the derivative of a tensor? Is it a tensor? And the answer is no. A tensor is a tensor if it transforms as a tensor. This is a non-tensor in general because it doesn't transform as a tensor, and I need to prove this now. Yep. So let's do it. So I'm going to begin with the left-hand side. Again, this is going to be the point at which special and general relativity diverge. So here we have an arbitrary mixed rank tensor, which I now want to take the partial derivative of with respect to x superscript r prime. I know that this is a tensor, and I'm asking the question, is this a tensor? Well, the notation if we unpack it, is d by dx superscript r prime of this object that we know to be a tensor. And since we know this object to be a tensor, it will transform as a tensor. Yep. So I can write the primed tensor in square brackets, but that's going to be the same as the tensor with all unprimed indices. But then I need to multiply by my partial derivatives. Remember that our p's that I'm writing now, we have the notation that this p stands for partial derivative. This is the derivative of, in this case, the old coordinates, the x coordinates with respect to each new coordinate. Yep, with pj prime j similarly defined. So these are the partial derivatives of the old coordinates with respect to the new. And remember, when you do coordinate transformations from an unprimed coordinate system to a primed coordinate system, then every coordinate in one system is considered as a function of all other coordinates in the other system, right? So I'm now going to hang my p's off, and since this is the indices have got a balance. Yep, the indices have got a balance. So this I must be gotten rid of. I get rid of it by summing over it with Einstein's summation convention. I have an I prime upstairs. The k has to be gotten rid of. It's summed over, it's gone. Replaced with a k prime upstairs. And notice that the upstairs coordinates depend on the derivatives of the new coordinates with respect to the old. Conversely, the lower coordinates, L primes, I want to get rid of this L. So it's gone, it's summed over. I wanted L prime downstairs, there it is. Notice derivative goes the other way. Derivatives of new with respect to old with respect to new coordinates. Dot, dot, dot. I want to get rid of the n downstairs with an n upstairs and replace it with an n prime downstairs. So this is the derivative of a tensor. We're asking the question, is this a tensor? Now I'm going to make use of the chain rule. I always hesitate because I forget the names of all these rules. I want to use the chain rule here now. How do I apply, how do I apply the chain rule here? What I'm going to do is add another p. Yep, I'm going to make use of the fact that, and I'll just write it over here because I'll use it in a second. Here I'm differentiating with respect to x superscript r prime, but I want to be differentiating with respect to x superscript r, and I can do this with the chain rule. Yep, I can do this with the chain rule, and that would be nothing more or less than d by dx superscript r times this p, r prime, an r upstairs, and this is effectively downstairs because it's upstairs in the denominator. They're summed over. We have the r prime downstairs, which is the same as an upstairs r prime in the denominator. So I can turn my partial derivative with respect to r prime. I can just wipe out the prime. But the price that I pay is I need to make these brackets slightly bigger, and I need to add an extra p. So now we can go ahead and differentiate each term in the square bracket. Sorry, the entire product in the square bracket. We can go ahead and differentiate it with respect to x superscript r prime. X superscript r, sorry. So let's do it. Now this is a product rule. Okay, it looks crazy because there's an arbitrary number of tensors there, but it's still the product rule. Go back to basics. If you have a times b considered as a function of one variable, and you differentiate with respect to that variable, the product rule says differentiate the first, leaving the second alone, differentiate the second, leaving the first alone. If you have a product of three such functions of one variable, you just stick the derivative on each term successively. Differentiate the a, differentiate the b, differentiate the c, and this can be applied recursively to any number of products. Same thing here, right? Here we're differentiating. Sure, it's in an n-dimensional space, dot, 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 but we're still differentiating. Product rule still works. I can differentiate the first object. I can differentiate the first object, which is going to be a comma R, leaving everything else alone. Plus, I then go ahead and differentiate the second object. Yep. Leave the first thing alone. Differentiate the second object. And this is the point at which I get sad, right? I get sad, comma R, right? I start differentiating the second object and write all this other guff. Then I start adding extra terms where I differentiate each of these P's. I'm sad for the following reason. Let me just write this left-hand side over here. Actually, I shouldn't be sad. I've discovered something profound, right? I shouldn't be sad. I look at this expression here, and I ask the question, how does the derivative of a tensor transform? And that's how it transforms. But this is not the tensor transformation law, right? This is not the tensor transformation law. Therefore, the partial derivative of a tensor is a non-tensor. I'm sad at these terms because if they weren't there, then this first line's beautiful. This says that the partial derivative of a tensor transforms exactly as a tensor. We had an extra R prime subscript index, so we had an extra P. This first line is the transformation law for a tensor, but this stuffed it up, right? Now, the P's, as I've emphasised before, are the derivatives of the new coordinates with respect to the old, or the old coordinates with respect to the new. If, and this is a big if the coordinate transformations are linear, if the new coordinates are linear functions of the old, and conversely, well, we've differentiated once a linear function, so if we differentiate it twice, which is what's happening here, P, we already partially differentiated the new coordinates with respect to the old. If you go ahead and differentiate a second time for linear transformations, you're going to get 0. So if your xj are linear functions of the xj primes, and conversely, if you restrict yourself to linear transformations, then this term disappears. In special relativity, our transformations will be linear. The Lorentz transformations are linear. In general relativity, that's not true. So this is a point at which special and general relativity diverge. Just as an aside, if I was teaching general relativity, I'd say the derivative of a tensor is not a tensor. I don't like that. I want to generalize differentiation so that the derivative of a tensor is a tensor. Question, how do you alter the definition of a derivative in order for it to be a tensor operation, producing tensors from tensors? This, by the way, is called a covariant derivative. Unfortunately, the word covariant has two distinct meanings. Covariant index, downstairs index, but if we say that a system of equations is Lorentz covariant, we mean something different. We mean that it's unchanged in form under a Lorentz transformation. Unfortunately, those are two distinct uses of the term covariant. The covariant derivative is an alternate form of the derivative, a more general form of the derivative, which is producing tensors from tensors. That's, by the way, the point at which curvature enters, space-time curvature. That's a very, very fun story, but it's not a story for this course. So we're assuming linear transformations at this point. And for linear transformations, the partial derivative of a tensor will be a tensor. By the way, in mathematics, these are called Cartesian tensors. If you restrict yourself to linear transformations, then you're talking about Cartesian tensors. I want to give a fifth example of tensor algebra, the so-called quotient rule. And with all elements of tensor algebra, this has a property of producing tensors from tensors. Suppose I gave you some equation, A equals BC. and it had some indices flying around, I, J, K, L, and the indices are balanced, right? If they didn't, it'd definitely be a wrong equation. And suppose I was to tell you that A is a tensor and C is a tensor. What I claim and what I invite you to prove, again the proof is trivial from the definition of how a tensor transforms. If A is a tensor and C is a tensor, then we can loosely think of B as the quotient of A and C. The quotient rule says, if you have an expression, an example of the quotient rule in action, sorry, says, if you have an expression like this, where you have tensor on one side and all the quantities on the other multiplied together are tensors except for one of them, then the odd one out will be a tensor. We can loosely think of B as a quotient of tensors A and C. I'm not going to do the division because sometimes this will vanish in some frames or some component thereof at some point. The point is that B is a tensor if A and C are tensors. I haven't stated that in general. You might want to state the general form of this so-called quotient rule, which can loosely be stated as the quotient of tensors is a tensor. Now we're still in our n-dimensional space, and there's been no special structure assumed in this n-dimensional space, which I gave the name following Windler of V superscript n. But many of the spaces of interest and the spaces that we'll work with, which is space-time, are so-called metric spaces. Beautiful subject in pure mathematics, by the way. And metric spaces assign some distance, or some rule which assigns a distance between pairs of neighbouring points. So if I had a pair of points, let's say P and Q, in this n-dimensional space, and if they were infinitesimally close together, so in some coordinate system, if I subtract the first coordinates, I'd get something infinitesimal, dx1, and I subtract the second coordinates of each of these, I get an infinitesimal dx2, all the way up to dxn. And these are going to be infinitesimals in some coordinate system. If we can, we're now going to equip this space with a metric with a way of measuring a distance, and this is a generalisation of the concept of squared distance. I'm actually going to give it the same symbol as the squared interval, because a squared interval will be a special case of this. We're going to have some object, which you can think of as a matrix. Here's our differentials. Remember there's an implied double sum here. This object here, okay, this is a power 2, it's not an index, this is ds squared. These, on the other hand, are superscripts. There's an implied summation here. This object is a tensor, it's a rank 0 tensor, it has no indices. Every observer will agree on this. It's a geometric invariant. These were our archetype, that was our archetypal rank 1 contravariant tensor. This is a product of our archetypal rank 1 contravariant tensors. And the product of tensors is a tensor, so that's a tensor. This is a tensor, therefore by the quotient rule, this is a tensor. And it's called the metric tensor because it assigns a generalised distance. In general, by the way, this will be a function of the space-time of the coordinates. Now, without loss of generality, you can assume that this is a symmetric matrix. In other words, if you flick the indices around, you get the same thing. If that's not, to make that point clear, write this out explicitly. The only condition I'm going to make on G's, I mean, ultimately they're going to be constant for us, by the way, but I'm going to make the condition that this matrix have 0 determinant. We write this out as a matrix. I want that, sorry, a matrix to have a non-zero determinant. Have a think about why. Now, the spaces equipped with such a metric are called pseudo-Riemannian. After the mathematician Bernard Riemann. So pseudo-Riemannian spaces. Now we can speak of a space as being strictly Riemannian if this ds squared is non-negative. Yep, if it's non-negative. However, we're going to allow ds squared to be both positive and negative, and so we've strictly got a pseudo-Riemannian space. I don't want to say pseudo-Riemannian, I'm just going to call it Riemannian space. Yep, so Riemannian space. Now we called rank 1 tensors, rank 1 contravariant tensors, for example, A subscript, superscript I. We call those vectors in the tensor sense of the term. Since these are geometric objects, which is the whole point of tensor analysis, I'm going to use a vector notation and call this a bold vector A. So if you were to give me two vectors in our n-dimensional space, we can adopt language reminiscent of vectors. In fact, these are generalized vectors, and talk of the dot product of two vectors. And our metric tensor is going to help us work out this generalized dot product. Again, there's an implied double summation here. As with vectors, if two vectors have a dot product of 0, then we say that they're orthogonal. Similarly, this is a generalized dot product. If this equals 0, then we say that these vectors are orthogonal. But again, these are vectors in our n-dimensional pseudo-Riemannian space. And this is not Euclidean space, right? So for example, we can happily have dot products being negative. I lied when I said there was 5 elements of tensor algebra. There's actually 6. One more element of tensor algebra, number 6, is going to be raising and lowering of indices. And we can actually use our metric tensor to raise and lower indices. So for example, if I have a rank 1 contravariant tensor such as A superscript j, if I was to multiply by the metric tensor, there's an implied summation over j. So whatever's left, the only free variable is an I subscript. I want to give this a name. I'm going to call it A. This is the same geometric object, right? And this relationship is invertible, actually, because G has 0 determinant by demand. This relation is invertible. This is the geometric object. This is the stick that exists independently of how you choose to coordinatize it. This is a contravariant representation of that object. This is a covariant representation of the object. We could change reference frames and stick primes on these things. It's still the same geometric object. And this raising and lowering is letting you transform from a covariant to a contravariant representation of this geometric object. I did make a distinction between vectors and one forms previously. You might want to have a think about how that's consistent with what I've just said. This ends our discussion on tensors as given in Rindler's appendix. And I emphasize this stuff is difficult. It takes a lot of getting your head around. So we've got the machinery. We've got these beautiful tensor formalism, which we now want to apply to the remainder of the course. One perhaps surprising thing is that even though we have boards full of full-on equations here, often tensor calculations have a certain lightness of touch, in the sense that sometimes you can almost get away with not calculating, invoke tensor concepts, and you can almost write down answers on inspection. As one example, the relativistic energy momentum mass relationship. Remember that E squared equals P squared, etc. Energy of a free particle, magnitude of its momentum, rest mass, m naught. That can be derived, that was derived in a fairly ugly way earlier. The tensor derivation is one line. You write down a certain quantity, which is the generalization of momentum, and then you write down the answer. So this is an example of tensor algebra, tensors at work. Many of the calculations, a very large number of them, are actually going to be a lot simpler than it might appear from what's here. And we'll see this. Now we want to take this machinery of tensor analysis and apply it to relativity. So we're now moving over to section 19, which is space-time and 4 tensors. So space-time is 4-dimensional, yep. And when we speak of a 4 tensor, we're talking about tensors which live in this 4-dimensional space-time. In fact, these are qualified tensors. Tensor is a tensor if it transforms as a tensor under an arbitrary transformation. We're restricting ourselves to linear transformations. We're cutting down capital N to 4 dimensions. And we're only going to consider one class of transformation, which is the Lorentz transformations. Strictly speaking, I should call these Lorentz tensors. We could also call these 4 tensors, but I'll often just lapse and call them tensors. Strictly speaking, they're tensors, the Lorentz tensors, because they transform as a tensor under the Lorentz transformations, where the new coordinates relative to the old, and conversely are given by Lorentz transformations. These are 4 tensors. Now remember, way back, we introduced a squared interval, this invariant, this geometric object. And if you had 2 events close together in space-time, P and Q, and the difference between these, just like over here, we had a delta t, and a delta x, and a delta y, and a delta z as a difference between these space-time coordinates. We agreed in one frame you'd assign these quantities. In a different frame it'd be delta t prime, delta x prime, etc. Different inertial observers would not agree on the coordinates, the space-time coordinates of this difference vector in space-time, but we learned that they would all agree. By definition, this squared interval, c squared delta t squared minus, they would all agree on this. So if I was to replace delta x, y, z and t with their corresponding prime quantities, sure they'll be different in different frames, but this object here will be the same. If we pass over to infinitesimals, we'd have ds squared equals c squared dt squared, etc. So we passed over to infinitesimals. And again, I emphasised this as a geometric object. Now, if we were in 3D, and if we had a Euclidean space, a space where Pythagoras' theorem holds, you'd have x squared plus y squared plus z squared equals distance squared. This is a generalised distance squared, but you need to be very careful. This is not a Euclidean space. This is not dx squared plus dy squared plus dz squared plus dt squared. If there was a negative here, I could just shove a negative out the left-hand side and say negative ds squared is dx squared plus dy squared plus dz squared plus c squared dt squared. And the c could just be absorbed into a redefinition of time, and it would look like Euclidean space. It would look like a 4-dimensional version of Pythagoras' theorem. This is not a Euclidean space, this is a pseudo-Euclidean space, because the sign of the dt squared is different to the x, y, z. So if anyone tells you that in relativity space and time are treated on identical footing, they're wrong. They're treated on a similar but quite distinct footing. And the fact that this is not a Euclidean space, in Euclidean space there's no preferred direction. Right? Dx squared plus dy squared plus dz squared, there's no preferred direction. This stick is the same length as this stick. Try that in space-time. If I was to have a stick in space-time and I was to rotate it in space and time, its length would actually change. The point here is that because of these bloody negative signs, they're beautiful negative signs, it's intrinsic to space-time. Space-time possesses a certain anisotropy which is utterly different to space-time. This is not a Euclidean space, it's pseudo-Euclidean. We can, for example, have 2 events that are distinct, different x, different y, different z, different t, and the ds squared is going to be naught. Yep. So pseudo-Euclidean space. I've already emphasised that a tensorial description of the physical world is natural, because tensor equations have the property of having the same form in all inertial frames. This squared interval is a rank 0 tensor. We want to tensorialise. We have a very ambitious program to tensorialise all of physics. But to begin with, I want to make the point that space-time coordinates x, y, z, t is going to be a position vector in our 4-dimensional space. And I want to use tensor notation now. X naught is going to be the same thing as CT. This is a superscript. We're introducing tensor language here. X superscript 1 is going to be x by definition. X superscript 2 is going to be y. And similarly for x superscript 3 being z. So these are going to be our space-time coordinates. And we know that these things transform according to the Lorentz transformations. But these coordinates are going to be tensors. These coordinates are going to be tensors. Now we're going to use Greek indices. When we have a Greek index, upstairs or downstairs, it's going to take the values 1, 2, and 3, and naught. by definition, by notation. On the other hand, so for example, x mu would take the values 0, 1, 2, 3. Our space-time coordinate could be written as x superscript mu in some frame, some inertial frame. On the other hand, if we use Roman indices, such as j or k, x superscript j, for example, then this can only take the value of 1, 2, and 3. So Roman indices only run through the space coordinates. Greek indices run through both the spatial and the temporal coordinates as a point of notation. So our infinitesimal squared interval can be written in tensorial form. You know, we already know this is a rank 0 tensor because it transforms as a rank 0 tensor. In other words, it doesn't transform at all. Yep. I argued earlier that the metric was a tensor. Infinitesimal coordinate differences are the archetypal rank 1 tensors. If we didn't know that this was a tensor, we could still say that's a tensor. This is a blueprint tensors. Product of tensors is a tensor. Hence, by the quotient rule, that's a tensor. Now, given the form of ds squared, we can write this thing down. You can actually write down immediately the 4x4 matrix representation of this metric tensor, G subscript mu nu, and it looks like as follows. All other elements are 0. I'll just write that as this. So this is our metric tensor. Dot products in space-time. If I give you one rank 1 contravariant tensor, which is a tensor under Lorentz transformations, I call that a Lorentz tensor, or a 4 vector, because it only has one component, it's rank 1, I call that the boldface A. Similarly for B subscript superscript mu. Again, the representation on the right emphasises it as a geometric object. We can dot product these two things. Yep. And when you do that, as we learned earlier, we use the metric. Yep. Implied summations, as always. Now, if we were to write A out explicitly, that would have 4 components. Similarly for B. When you dot product them with the metric, what you do not get is A0, B0 plus A1, B1 plus A2, B2, etc. There's this difference in signs here. What you actually get is A0, B0 minus A1, B1 minus A2, B2 minus A3, B3. By the way, dot product produces tensors from tensors, right? This produces tensors from tensors. This is a rank 0 tensor. This is an object upon which all inertial observers agree. You go to a different coordinatization of space-time, you Lorentz transform. Each of these 8 numbers will in general be different, but when you form this dot product, which is a rank 0 tensor, a Lorentz invariant, a constant, an absolute, right? Then you'll get the same value for this combination of the various components. As a special case of our dot product formula, if we set A equal to B, then we can have the dot product of A with itself, which I'll write as A squared, and that will be A0 squared. Again, our famous minuses, A1 squared minus, etc. That's all I wanted to say about section 19. I want to now move on to section 20, which is called world lines and light cones. Section 20, world lines and light cones. I won't write it out, world lines and light cones. So imagine you have some point particle which is moving through space and time. Now we could say it moves through some one-dimensional trajectory in space, but actually it's a one-dimensional trajectory in space-time. This point particle will trace out some one-dimensional trajectory in space-time, and we give this one-dimensional trajectory in space-time a name. We call it the world line. Now, if I take my watch off, in fact, I'm not left-handed, but let's go for it. Imagine this is the point particle, and it could be moving around, and you could parameterize its position in space-time according to your approximately inertial frame, your x, your y, your z, your t, and you could parameterize this object like that if you wanted to. By the way, a trajectory is nothing more than a sequence of events, right? A series of dots in space-time. Connect them together, and you have the world line, the one-dimensional trace that this point particle follows through space-time. But another way, a natural way to parameterize it, remember the idea of a proper quantity, the proper value of a quantity is the value that quantity takes in the rest frame. So the rest mass, the rest mass is the proper mass, the rest length is the proper length, and so on. Well, a natural way to parameterize this point particle is to stick a watch on it, and sure, it's going to be an accelerated frame, but nevertheless, it's got a watch, and that watch will read a particular time in this accelerated, in general, frame, right? So we call this the proper time. So here is the space-time coordinate of this point particle, but it's a sequence of space-time coordinates, a sequence of events, and we could parameterize those by the proper time, the time that will be read on a wristwatch that is attached to that point particle, proper time, and we give it the symbol tau. So we can parameterize this world line by x mu, we can parameterize it by tau. Again, our Greek indices will run through both temporal and spatial coordinates. Now I could choose, if I wanted to, some point on this trajectory, and this is actually any point on the trajectory, and I could call this P. And according to some inertial observer could erect an XYZ coordinate system here. Now I can't draw 4D, so let me have two spatial coordinates, delta x and delta y. I use deltas because this is an arbitrary origin P, and I'm thinking of any point in this space, any point Q, for example, on the world line. A point Q on the world line is really a difference vector from this arbitrary origin, so I'll coordinatize it by delta x, delta y, and delta t. But following the box in the top board, I'll give the dimensions of time the units of length. So here we have our world line. We've chosen a particular point P on that world line, and we're coordinatizing the remainder of the space-time with these difference coordinates. Now, if you had an expanding shell of light here, in fact, let's have a quick aside. I'll throw a duck into a pond, and suppose the duck cannot swim faster than the speed of the water waves. So, sorry, you gently place your nice pet duck at the point X. This is the pond being looked at from above. And when you place the duck in the pond, there'll be some circular expanding shell of water wave. But suppose that the duck cannot travel at or beyond the speed of the water wave. So the duck can swim around. It started at this point X, but no matter how much it swims or how fast it swims, it can only swim as fast as it can. It will always be inside this expanding water wave. Now, if I was to stack these, so time here is running from left to right. If I was to imagine stacking these, this would actually trace out some trajectory inside a cone, yep, just like here. Except instead of a duck, it's the event P. Instead of the expanding water wave, it's now an expanding light wave that corresponds to a click at this particular point P in space-time. So, if I was to have an expanding shell of light that was emitted corresponding to the event P, then the world line would always be constrained to lie inside this cone. This cone is called the light cone. and this is in fact called the forward light cone. So since material particles cannot travel faster than the speed of light, all point particles are constrained to have their trajectories lying within the forward light cone, which is placed at any point P on that said trajectory. We can extend the light cone into the past. So expanding spherical wave emanating from the event P, contracting spherical wave converging on the point P. Now this construct, this idea of a light cone, which is erected at each point on the world line of the particle, has something important to say about what you might call the causal structure of space-time. Yep. So here we have our world line, yep, of our particle, always constrained to lie within the light cone, forward and backward erected at any point P. Now let's talk a little bit about cause and effect, about causality, and ultimately about the causal structure of space-time. But before we do that, remember our equation regarding the invariant squared interval. This light cone, as I've emphasised, is the equation of an expanding spherical shell of light. But so is this. So this is, oops, the equation for an expanding spherical shell of light. If I give you a particular point P on the world line of a particle, and a particular point, let's say M, which lies on the forward or backwards light cone, there'll be a difference in some frame of reference between these two events, which will be delta x, delta y, delta z, delta t. That will obey this thing equaling naught. That, sorry, is an equation for an expanding spherical shell of light. But this was a squared interval. This was a tensor. So we've actually got the squared interval vanishing between any pair of points that can be connected by a light signal, between any pair of points that lies on a light cone. Interesting. Even more interesting is that this construction talks to the causal structure of space-time. Yep. These coordinates are a bit of a fofy in the sense that this event is something that exists independently of how we coordinatize space-time. Ditto for this, for this world line, and ditto for the light cone itself. So let me draw it in a coordinate-free way. I'm not going to even put a coordinate system there. Everything that I'm doing here is geometric objects. Everything is a geometric object here, no coordinates. And the key point is, you re-coordinatize space-time and you'll screw up the description of the coordinates that lie on the light cone and everywhere else. But this is a geometric object upon which I've just drawn it as some hypersurface. This light cone is a hypersurface. It's actually a three-dimensional surface embedded in 4D, which I've drawn as a 2D surface embedded in 3D because of my inability to do four-dimensional diagrams. But this is a geometric object. I've trashed the coordinate system and it's still there, right? This is an absolute construct, and in particular, it actually delineates the causal structure of space-time. What do I mean by that? What I mean is, every point inside the forward light cone, here's one world line, here's a second world line, here's a third world line. Every possible world line that passes through the event P is constrained to have its future lying within the forward light cone. The inside of the forward light cone is the maximal set of events that can be causally influenced by the event P. So this interior of the forward light cone is called, we've given it a name, these are absolute constructs. This is called the absolute future. And again, note the anisotropy. I mentioned earlier that space-time has an anisotropy, which is utterly unlike that of Euclidean spaces. This causal structure that I'm talking about wouldn't be permitted if that anisotropy didn't exist. So we have the absolute future, the maximal set of events inside this forward light cone. In fact, inside and on the forward light cone, because you could have a light signal from P reaching any point M on the light cone. So the set of points inside and on the forward light cone of any point P in space-time is the absolute future, the maximal set of events that can be causally influenced by the event P. Similarly, every point inside and on the backwards light cone is spoken of as the absolute past. This is the maximal set of events in space-time that can have a direct causal influence on the event P. There are points L, for example. There can be no direct causal link. There might be correlations, but there can be no direct causal link between an event P and an event L, which lies outside the light cone. And so we have some notation to capture what I've just said. If you give me a pair of events, then I'll be able to ascribe a certain delta S squared to them. I'll be able to ascribe a certain delta S squared to them. So give me a pair of events with a particular delta S squared. Again, I've just argued that we have a forward light cone that would correspond to delta T being greater than naught. So if delta T is greater than naught and delta S squared is greater than naught, this would correspond to the absolute future. And I invite you can quickly show this, right? I've drawn the picture of it, but I'm claiming that this corresponds to a pair of events whose delta S squared is positive and the delta T is positive. On the other hand, if we were to have delta S squared greater than naught and delta T less than naught, then I would call this the absolute past. And just two final points actually. And this is notation, if you have a pair of events in space-time, and if delta S squared equals naught, delta S squared is less than naught, or delta S squared is greater than naught, we give names to these things. If delta S squared equals naught, we would call this pair of events separated by a light-like interval or a null interval. The term light-like emerges because this pair of events can only be connected by a light signal. It's called null because delta S squared vanishes even if they're distinct points. Any pair of points on the light cone has a delta S squared which vanishes. Delta S squared less than naught, these things are called space-like. And I invite you to show that this corresponds to pairs of points that can have no causal influence on one another. Lastly, if delta S squared is greater than naught, we call this time-like. And these things can, in principle, be connected by a material particle. Hope you enjoyed that lecture. Thank you.